Our final presentation then for this morning is from Professor John Campbell. Now, I mean, John needs no introduction from me, so I think the only thing I will say is that I would say John's evidence-based approach, going back to first principles, changing his mind as he learns more, adapting, the appliance of thought and science to make quality castings can only be commended. John, over to you.
Thank you very much, Pam, and good morning to you all. Many of you will have heard me speak before, and so a lot of what I'm going to have to say at the beginning is for those who haven't heard. So those who have heard me talk before, you can quietly go to sleep for the next 5 minutes. But most of you might, or those of you working in the industry will have seen this checklist of mine, this 10 Commandments by JC, that this very obviously the use.
Are you okay?
I'd much rather shout.
Is I happy to shout? Fine, that's fine. I'm only thinking of you.
I do hope you can all hear. Yeah. This obvious one of using good quality metal, if you're in the aluminium industry, you fail instantly. And it's really difficult to get over this, and we haven't time to talk about it today, especially now. But anyway, then you know these things, not too fast, we don't want turbulence, not too slow, it must not stop, and we must not get bubbles in, either air bubbles or core blow bubbles. And then there are other things too. What I find the wonderful ability nowadays we have to simulate the casting on a computer, which we're going to hear about more later today. Mainly I see that dealing with these sorts of things of feeding and of shrinkage, but in dealing with this part, which is to do with the quality of the metal, the computation has got still a long way to go. So let's move on quickly. This is how we want to fill a casting, and when we look down into a mould and we see it filling, any of you who've worked in a foundry know that you can see the oxide film, you can see it moving to one side as it comes up, it's all the while breaking and moving to one side, so that surface oxide becomes the skin of the casting, and you get a lovely quality of metal inside. There's no oxide inside the casting. Now, unfortunately, that's not how we make castings. We tend to make castings like this, where it's poured in and it's churned around, and that's an extremely dangerous situation as far as the quality goes, because, again, nearly all of you have seen this. Anyone want to do this in place of me? Here's the oxide on the surface. Here's air, here's metal. Unfortunately, this junction of the two is a solid, normally. And this gives us problems. The top is a dry surface, like sandpaper or something, under the microscope. But underneath, it's 100% wetted. We're in atomic contact under here. And the trouble is, every time we fold in the surface, it always goes in dry side to dry side. You can't get it any other way. This is a law of nature, that the dry sides come together, which means there's no bonding, which means it's a crack floating about now inside the liquid. Now, by turbulently pouring our castings, we're cramming them with cracks. And then we wonder what's happened to the properties. I mean, these things are so pathetically obvious, it gets me furious. I mean, I worry that they're too simple for people to understand. And this is a problem. There's an enormous simplicity in this subject. So I now talk about the whole concept of entrainment as being the key aspect of the getting quality into castings. And so this name, entrainment, I use it all the time now, and these particular entrainment defects are what I call bifilms, which are double films, which are always acting as cracks. So every time you see oxide in your metal, you know it's there as a double film. It can't be there as a single film. It has to be doubled so you know every oxide is a crack. Okay? These things are, let's say, they're too simple to understand easily, but bear with me. And the other thing, we see lots of porosity in castings, and people whinge on about the hydrogen content and other nonsense like this. But at the end of the day, most of the porosity we see are these things that you have to learn this special technical name. It's called an air bubble. We've got it. Okay, so these are the critical things. Biofilms and bubbles, they are the entrainment problems. So this is the kind of thing we see, and the whole business of filling castings is so messy and turbulent. It's amazing we ever get any decent castings. And I keep saying this. And this is a radiograph of two small cups of metal, one poured under 1 atmosphere, one poured under reduced atmosphere, and under the reduced atmosphere, we expand these things, and I forgot to say, in the turbulence of pouring, this happens. The turbulence gives you a compact biofilm, which happens, and we see it here. These tiny shadows are the compact biofilms. And then when we reduce the pressure, then they open. Of course, you have this special scientific experiment. I have a biofilm here. It's a parallel bit of film, two films, with no bonding between the two films. And if we increase the pressure on the inside, it does this amazing thing, which has happened here. And this happens in our castings totally naturally as a result of shrinkage. The biofilm opens again, and as it continues to fold open and get bigger and bigger, so the properties come down and down, which is why heavy section castings have poor properties. Light sections have better properties because the biofilms don't have time to open before it goes solid. Okay, we need to rush on, and this epitomizes to me where our foundries currently are. And I mean, it's not this chap's fault that he's ruining the metal. It's the design of our foundries is all wrong. And every time I hear now of a new foundry being built, I think, oh no, another lost opportunity. And we have to design our foundries to avoid pouring and to avoid turbulence, because we're just manufacturing difficulties for ourselves and limiting the whole of engineering. When you think that all our metals are cast full of biofilms, if all our metals are showing properties which are a fraction of what they could be. And I think we could revolutionize engineering if we got rid of this sort of thing and redesigned our foundries. So if we now want to get the metal into molds, how are we going to do it? And we can just pour it in the top, and that's really bad because obviously it's turbulent. We could bring it at the side, that's also bad. We bring it in at the joint, which is almost certainly bad. Sideways at the bottom might be acceptable. Coming at the bottom is, you can work with this. But if we bring it from the bottom without ever pouring once, and only come up against gravity, this is in a league of its own. So I would like to see the whole of the industry never pouring any metal ever again. And our foundries should be designed never to pour metal. Pouring metal is extremely damaging to the metal. And I'd like to see them all moving to counter-gravity. Now, I'd like to see all of you putting that into your next 5-year plan. In the meantime, we have to live for the next 5 years. So we'll retreat and look at this and to see what we can achieve using gravity, but using it carefully. So, whoops. You see, here we're coming in at the bottom for castings, so we're correctly coming in at the bottom to try to fill up, but this is obviously too fast, so even when we come in vertically this way, we're coming in at the bottom, trying to fill uphill, but, I mean, frankly, failing miserably. So the speed needs to be controlled, and there's plenty of both theoretical and practical work which tells us that the speed has to be less than about a metre a second. And not only do we have to control the speed, we have to control air entrainment. So, the various ways, we have a look at the different velocities that we can come in. If we come in at 0 velocity, the metal is, you know, beautifully safe, but it's just a way of manufacturing empty molds, you know, which is not good for production. If we come in too fast, the metal leaps into the air and falls back, and you're now manufacturing biofilms and bubbles. But there is this critical velocity where the metal's just supported by its surface tension. And this is about the ½ metre a second, which you can push to about a metre a second. And in that bracket of velocities, you can make actually castings without entrainment defects. So, yes, this is the kind of speed we want. And it's this speed for practically all the liquid metals, whether it's titanium or aluminium steels. So, what happens now when we try to pour our metal? We're coming in at the bottom. We want to come in at the bottom, but what's happening here? This conical basin acts as a pump, and any chemical engineer would know that. And what a chemical engineer would know, we're dragging air from the environment and forcing it down through the cone, and this mixture coming down here is a mixture of about 50-50 metal and air. Now, I'm going to have to, how much time have we got? I'm running out of time, but I have to show you this one. This is the simulated, many of you have seen this before, but I'm sorry. Let's move on just one picture. If we get rid of the conical basin and put our ladle directly on the mould, we eliminate the basin, and I call this contact pouring. And you see, because we don't get air in here now this whole thing is pretty well free of air. So I'm going to do a contact pour now for a simulated lung full of liquid steel, just to see what the volume is. And it's at this point I always feel completely ashamed. I mean, you wouldn't think I would go to the gym every day, would you? Anyway, that's it, you know, that's a simulated lung full. And now I'm going to do a conical basin filling with the same simulated longful. Okay. I mean, it is dramatic, isn't it? And here, the whole world uses conical basins for filling molds. It's used everywhere, all over the planet. We're all wrecking our castings. Every day, nearly every casting is wrecked. So, and here, we'll come back to this particular layout, but let's move on quickly. There are ways to get round it. not using contact bore, and this is using an offset step basin where you get the bubbles can go up here, and then so bubbles go one way, metal goes down this way. Unfortunately, you're entraining the surface oxide, so we are entraining bifilms, and the bifilms don't have time to detrain, so the bifilms go down, only the bubbles go up. So this is only half the solution. However, there is a way to use the basin very, very carefully, and my good friend in Canada, Bob, gets his ladle right up to the edge of his pouring basin so that he's not actually entraining anything. The oxide is now stationary and the metal is moving underneath. And that's just with paying that care, he now gets properties which about 18% elongation as opposed to scratching around with a few percent of elongation in aluminium alloys, which most of us do. And but I say to him, why are you only getting 18% elongation? Why aren't you getting 30% or 50% elongation, 100% even? And these high percentages, I'm sure, are attainable, and they're attainable in steels. Most steels have about 50%. And that's because they detrain their bifilms rather quickly, because the density difference is quite big, so the steel cleans itself quickly. That doesn't happen in aluminium, which is why aluminium has such poor elongations most of the time. Anyway, one of the big ways forward that was being promoted by me and other people a few years ago was the Vortex Gate, and it controlled speeds wonderfully. So metal would hurtle along here, along the runner, zoom around in the disc at the bottom, and then centrifuge its way up here, and then you'd have a filter on the top to take out most of the rotational velocity before it comes through the gate and into the casting. And this thing was magnificent in reducing speeds. And the speed is brought down by the ratio of just the area of that to the area here. So you could easily get 10-to-1 reduction in speed, which was brilliant. And we thought this was the great way forward to make castings. Now, unfortunately, when we first pour, the whole system is full of air, and we want it full of metal, of course. And for those first second or two in the priming, the two are mixed. And so you have priming bubbles which are entrained in the system. And it's essential that we get rid of those. Now, unfortunately, the Vortex Gate doesn't do that. And that's because the bubbles come along here, they're centrifuged around here, they're centrifuged into the center and sit under the filter, where they have difficulties to get through because they're not buoyant enough. But then more bubbles arrive, the bubble grows, more bubbles arrive, it grows and grows until finally it's buoyant enough to force its way, and it forces through, and the bubble goes up through the casting, leaves a huge oxide bubble trail as it goes, and makes a great mess of the casting. So I can't recommend this, unfortunately. And so one of the systems which has come up, and which I've devised fairly recently, is this use of a flush or a tangential gate in which I plant the filter on top of the runner, so bubbles that come along tend not to sit under the filter. They tend to be pushed ahead. They're enabled to go ahead if they want, but they don't accumulate under the filter. And so this is quite good for keeping out bubbles, and it's also pretty good for reducing speed through the filter, and then it goes up. Now, when we look at in a plan view here, at the end of the runner, I put a spinner here. The spinner is marvellously effective. People used to put dumps at the end of runners to take cold metal. What they really were doing were taking damaged metal, hopelessly entrained metal because of the priming problems. Now, unfortunately, most of those dumps at the end had a reflected back wave along the runner, and so you'd fill the dump and then it would unfill and put all the mess all the way back along the runner. It would then go up through the gates and into the casting. The spinner doesn't do that. It gradually builds up, and so the metal rises in a progressive way, and it never reverses back into the runner again. So it takes all that material and keeps it in the track. But more importantly, it builds up its back pressure in the system slowly. And that means that the gate senses the back pressure and fills slowly under a gentle pressure. So we don't get the full head height from the sprue acting on the gate immediately. And that means that the gate fills slowly without jetting. And then when enough metal is now in the casting, now the spinner is totally full up to the top. Now the full head height comes on, and now the whole system fills up rapidly. Now, I'm sorry if that sounds rather convoluted, but we'll come back to it in a moment. I just want to mention this because this is in the title to the talk. I don't know who put this title to this talk.
It must have been you, John.
This is the Trident Gate, and again, my friend Bob in Canada is using this for all his castings nowadays. There's a filter here which encourages the priming bubbles to go straight on and not come through into the casting. And if some do come through, they then roll up the surface of the second filter and sit in the bubble trap. The metal goes through, and then this is the gate into the casting. And this whole thing here is a little block core, something about this size, just sits on the runner. And he's been using this for over 2 years now. And what he tells me is that he hasn't made, during this period, a single casting with a single defect in it. Now, these things really do work. And if I go back now to this layout, which is stepping back from the Trident Gate to this slightly simpler gate of using just the flush or the tangential filter, let the bubbles go. We've got our spinner here, which gives us the gentle back pressure to fill here. All this is capable now of making castings with 0 defects. Now, it's finally arrived. And this is the first time in history I'm able to stand here and tell you about this, because only this last week I've heard 2 reports from opposite ends of the world, one from Poland, one from the States. People have been testing this system, and they find, to their amazement, that it works. So I'm delighted that independent people are coming back to me now to say, yes, we can make perfect castings for the first time in history. So we're at a very important state. We're able to do this even with gravity. To be honest, we'd do it even better by counter-gravity. And the wonderful thing about counter-gravity, it's so easy to automate. And I've been working with a foundry using counter-gravity just recently, and the speed at which we could produce castings was so exciting. And all of these castings are perfect. So I think we're in the threshold of something really big, really important, that could change the whole of engineering. Thank you.